All right, these notes today are very simple, so we're just going to go through them quickly in this format. But what we're going to talk about today is the stoichiometry part of this unit, and there's three types of stoichiometry problems. The first one we're going to talk about regards Gay-Lussac's law of combining volumes. Of gases, which states that at a constant temperature and pressure, the volume of gases or gaseous reactants and products can be expressed as ratios of small whole numbers. And so what that means is, for example, in this chemical reaction here, notice first how they're all gases. That's very important. So if we're talking about two different things here, they both need to be gases for this to apply. But essentially what that means is 2 liters of this will react with 1 liter of this to produce 2 liters of this. And so we can think about these coefficients here, which if you remember, these coefficients are mole-to-mole ratios. We can think about them as volume-to-volume ratios as well. So again, that means 2 liters of hydrogen gas will react with 1 liter of oxygen gas and will produce 2 liters of water. And another example, if we had 4 liters of hydrogen gas, 2 liters of this would react with that, and it would produce 4 liters of water vapor. And so again, you can use those coefficients from the balanced chemical equation as a direct conversion from volume of one gas to volume of another. But let's take a look at letter B here. In stoichiometry calculations, where not all the desired reactants and products are gases, so not all of them are gases, this volume ratio will not apply. So again, if one of these here was a solid, for example, or a liquid, you couldn't use this ratio. We must remember that the balanced chemical equation will always relate amount in moles regardless of the state of matter. So essentially, if we're not dealing with only gases, we can use the fact that these coefficients also tell us the amount of moles. So 2 moles of this will react with 1 mole of this to produce 2 moles of that. And so what we can then do is just convert everything to moles, go from moles of one substance to another, and then convert it to grams or liters or whatever we want. All right, so for this next part here, now that we have established that we can use moles to go from one substance to another, what we can do is, for stoichiometry calculations involving gases, we often specify the quantity of a gas in terms of its volume at a given temperature and pressure. And so we'll always be given a temperature and pressure. And again, if we're given the volume, we're given the temperature, we're given the pressure, we can then use the ideal gas law, which is PV equals nRT, to determine the amount in moles. And we can do that from if we're given the volume. And this is the ideal gas law, but it's solved for moles. This is also the ideal gas law, but it's solved for volume. And so we can use the ideal gas law to convert to moles. And once we know moles, we can go from 1 mole of a substance to another. We can also determine the volume from the amount in moles. And so if we were to, say, calculate the moles produced, we can then take the moles, plug it into the ideal gas law to calculate the volume. Again, we would be given the pressure and the temperature to be able to do that. Now, the other thing that we can do is if gases are at standard temperature and pressure, which, quick reminder, the standard temperature is 0 degrees Celsius. The standard pressure is 1 atmosphere of pressure. We can use this right here to convert between liters and moles. So that's actually really easy. We can use the fact that 1 mole will be 22.4 liters, and again, that's for any gas. So if we're at standard temperature and pressure, we can use that fact to convert between volume and moles. And again, once we know moles, we can go from moles of one substance to moles of another. And that's pretty much it. So there's 3 types of stoic problems here. We've got our volume to volume problems. We have our problems that we use the ideal gas law, like which is right there. And then we also have our problems that are at standard temperature and pressure. And if it's at standard temperature and pressure, we can use the fact that 1 mole is 22.4 liters. Go ahead and watch the guided practice problem. What I will say is for this lesson, the guided practice problem are so important to follow along and pay attention to, because that is where we learn how to identify what type of problem there is, or what type of problem we're dealing with, and how to solve it. And so that's where we're really going to learn the material there. So have a great day.